we're going to talk about what it means for a graph to be symmetric. So there's three types of symmetry that we're going to look at. The first type is for a graph to be symmetric about the x-axis. A graph can be symmetric about the y-axis. And a graph can be symmetric about the origin. We're going to look at some examples of each one of these cases, and we'll also look at graphs that are not symmetric at all. So I think the best way to get started is to look at some of the examples we saw in the previous video and try to figure out if they're symmetric about the x-axis, y-axis, the origin, or not symmetric at all. So one example we saw, we actually plotted this graph, y is equal to 4 minus x squared. And this graph is symmetric about the y-axis. So what it means to be symmetric about the y-axis is if you look at the y-axis, which is right here, and you folded this graph along that line, if you have a mirror image on the left-hand side and the right-hand side, if these two are mirror images, then it's symmetric about the y-axis. So if you fold it and the graph lines up on both sides, so like folding it in half, you'll just get this piece here, then it is symmetric about the y-axis. If, for example, we had something like this is not symmetric about the y-axis. You can see if I folded it in half, what would happen? Well, then this piece here would be flipped here, and this piece would stay, and they're not going to line up. But if I folded this, and let's say I took this side right here, and I laid it on this side, you'll see that I'll just get this piece. Now sometimes we won't want to graph a equation, so what we can do is actually use the equation to figure out if it's symmetric about the y-axis. So to do that, when we have y is equal to 4 minus x squared, what you want to do is you want to see if you plug in negative x for x, and you get the same equation, then your graph is symmetric about the y-axis. So that what that means is wherever I see an x, I'm going to plug in negative x. So let's look at this right here. Plug in negative x. So we'll get y is equal to 4 minus a negative x squared. Now I'm going to simplify this. If you take a negative number and you square it, you're going to get a positive number. For example, if you take negative 3 and square it, this is negative 3 times negative 3, which is 9, which is the same thing as 3 times 3, or 3 squared. So this negative, when you have an even power like this, it goes away. So this is the same thing as y is equal to 4 minus x squared, because I can get rid of the negative because this is even. And this is exactly what we started with. So if you plug in negative x for x, and you get the same equation that you started with, then your graph is symmetric about the y-axis. So that's how you can tell. So I give you an equation, you want to know if it's symmetric about the y-axis, but you don't have a picture, and you don't really know what it looks like, you don't want to spend time plotting the points, just plug in negative x. So if you had something like y is equal to 4 minus x to the 4th, or y is equal to 4 minus x to the 6th, whenever you have an even power, it makes the negative go away. So it's going to be symmetric about the y-axis. Something else I could ask you about a graph that's symmetric about the y-axis. Let me erase this. Now notice, what I just said was, if you plug in a negative x, you'll get the same thing for y, right? Because when we plugged in negative x, the negative went away. So something else I could ask you on your homework, if I tell you that you have a symmetric graph, so I say, let y be an equation whose graph is symmetric about the y-axis. So I'm not giving you an equation, I'm just telling you that you have an equation that's symmetric about the y-axis. Suppose 3, 4 is on the graph of y. Give another point on the graph. So what did I say about the function? If we plug in negative x, we're going to get the same equation. Like this problem here, when we had y is equal to 4 minus x squared. If I know a point on the graph, like let's say on this one, if I plug in 1, for example, I get 4 minus 1 squared, which is 3. But I also know there's a mirror image on the other side. If I plug in negative 1, I get 4 minus negative 1 squared, which is 1, so 4 minus 1 squared, which is 3. So this one would have 1 comma 3 as a point, and also negative 1 comma 3 as a point. And that's what's going to happen here. Because you know this function, this equation here, is symmetric about the y-axis. If you plug in a negative, you're going to get the same equation. So another point on this graph would be negative 3, 4. Now this equation is not this one here, but I'm just saying if I just give you a random equation and I tell you there's a point on it, like this one, you can tell me one more point, and that's by plugging in the negative of this x. Okay, let's move on. Let's look at another example. This one's similar to our last example. This is x is equal to y squared. So before we had y is equal to 4 minus x squared. Here we're squaring the y instead of the x. And see what happens? It rotates that graph. And the vertex of the parabola is at the origin. Now, does this graph look symmetric? The answer is yes, it is symmetric, but it's not symmetric about the y-axis. So if we wanted to see if it was symmetric about the y-axis, then whatever we would have on this side should be on this side as well. This graph is symmetric about the x-axis. So here is the x-axis, and if we folded this graph in half, you would see that these two pieces would line up. Now, given an equation, you can tell if a graph is symmetric about the x-axis if you plug in negative y and you get the same equation. So a graph is symmetric about the x-axis if you plug in negative y for y and get the same equation. So our equation is x is equal to y squared. So look what happens with this one. X is equal to y squared. If we plug in negative y, we get x is equal to negative y squared. And again, we have a power that's even, so this can be simplified to x is equal to y squared. So when we plug in negative y, we get the same equation. And since that happened, we can tell that this is symmetric about the x-axis. So again, if you don't have a picture and you can't see if it's symmetric, all you have to do is plug in negative y. Now here we can see that this graph is not symmetric about the y-axis, and I'm going to show you how to do that as well. So if I ask you, is x equal to y squared symmetric about the y-axis? Well, from the picture, remember, if we look at the picture, we don't have the same thing here over here. So visually it is not symmetric about the y-axis, but we can also tell by looking at the equation. What do we do to tell if something's symmetric about the y-axis? Well, we plug in negative x for x. So we'll get negative x is equal to y squared. Now I don't have a squared here, so I can't get rid of this negative. And so this does not equal this equation here, because now I have a negative that doesn't go away. There's no way to simplify this to make this negative go away. So it's not symmetric about the y-axis. It's only symmetric when that negative disappears. So the negative would disappear when we put it with the y, but not with the x. Okay, let's look at another example. This one is y is equal to x cubed. Now, let's review. We had symmetric about the x-axis and symmetric about the y-axis. Is it symmetric about the x-axis or y-axis? The answer is no. Why is that? First off, let's do the y-axis. So if I made a dotted line here, and I took this piece of the plane here, and I folded it over. So let's say I put it over here. What is the graph going to look like? Well, this piece is now going to go here. So what I'll have is this graph, and they're not lining up. So it's not symmetric about the y-axis. Let's write that down. Not symmetric about the y-axis. You can also tell that because if you plug in a negative x for x, you get y is equal to negative x cubed. And when we take a number that's negative and cube it, we get a negative number. This is actually y is equal to negative x cubed. So again, we can look at negative 3 cubed. This is going to be negative 3 times negative 3 times negative 3, which is 9 times negative 3, which is negative 27, which is the same thing as taking 3 and cubing it and multiplying it by a negative, which is what I have here. This one is saying I have the negative of the number and then I cube it. This one's saying I take a number, I cube it, and then multiply it by a negative. So here the negative did not disappear, so it's not symmetric about the y-axis. Okay, let's clean this up. Is it symmetric about the x-axis? So this is not symmetric about the x-axis. Again, we can make a little dotted line along the x-axis. And if we flip this part of the graph and put it down here, what we're going to get is something like this. So we'll have this piece and they're not lining up. So it's not symmetric about the x-axis. And we can check this by using the equation. The equation is y is equal to x cubed. If we plug in negative y, we get negative y is x cubed, and this negative does not go away. Now there's one more type of symmetry, and that's something being symmetric about the origin. This graph is symmetric. Let me put is here. It is symmetric about the origin. And let me tell you what that means. Something is symmetric about the origin if you twist this. So if you take this piece right here and rotate it to here, these will line up. So you can see if I rotate this, this piece will line right up on this piece. And anything I have in this section will line up with what's in this section when you rotate it. If that happens, then you have a graph that's symmetric about the origin, which is what we have here. Now we can also test this by using the equation. So the equation was y is equal to x cubed. Let me move this over here so we can not see any part of the other graph here. So y is equal to x cubed. How we test if something's symmetric about the origin is if we plug in negative x for x and negative y for y, and we get the same equation. So to test the equation for symmetry about the origin, plug in negative x for x and negative y for y, and see if you get the same equation. So see if you get the original equation. If you get the original equation, then it's symmetric about the origin. So let's work with this one. We had y is equal to x cubed. I'm going to plug in negative y for y and negative x for x. I'm going to simplify this side. This is negative y is equal to negative x cubed. And then if I multiply both sides by a negative, I get y is equal to x cubed, which is the original equation I started with. So it's symmetric about the origin. All right, let's look at another example. How about this one? Now this was a problem we did as well. This is y is equal to 3 minus x. Now visually, we're going to test if it's symmetric about those three different types of symmetry. It's symmetric about the origin, x-axis, and y-axis, and then we'll also test it just by plugging in negative x and negative y. Okay, so is this symmetric about the let's say x-axis first. So x-axis, I'm going to write a question mark here, y-axis, and then let's also do origin. So for the x-axis, if we draw a line here and flip this, will the two pieces line up? Well, the answer is no. We'll get something like this. So no for x-axis. Y-axis. If I draw a line right here on the y-axis and I flip this piece over, will I get a mirror image? And the answer is no. I'll get something like this. So this one is also no. How about the origin? So if I let's focus on this piece here and rotate it, do I get the same thing here? The answer is no, I actually don't get any. There's nothing here. So you can see that if it was to work, I would have a line right here, and I don't have that. So the answer is no. Also, this piece here, if you rotated and put it here, you should have something like this. And you don't have that here. You have a parallel line, but you don't have this rotated here, because you can see that this is off the center, so it should be off the center on this side. So the answer is no. This is probably the hardest thing to understand visually. But we can also just check using this equation. We can check each one of these. So let's do that. Let's start with the x-axis. I'm going to start this one. So to check if something is symmetric about the x-axis, what do? We plug in negative y for y. So if you plug in negative y, this is what we started with. Plug in negative y. This negative doesn't go away. If you multiplied both sides by a negative to get rid of it, you'd get this, which is not the original equation. These aren't equal. So you can say it's not symmetric about the x-axis. No. Let's try this one, symmetric about the y-axis. What we need to do is we need to plug in negative x for x. So you can see y is equal to 3 minus a negative x becomes y is equal to 3 plus x, which is not the original equation. Instead of a negative x, I have a plus x. So it's not symmetric about the y-axis. What about the origin? Well, for something to be symmetric about the origin, you have to plug in negative x and negative y. So we get negative y is equal to 3 minus a negative x, which becomes negative y is equal to 3 plus x, and you can get rid of this negative if you want to, multiply this side by negative, and you can see that these two are not equal. So it's not symmetric about the origin either. Let's look at our next example. Here we have a circle. The equation of a circle looks like this. Is this symmetric about the x-axis, the y-axis, or the origin? Visually, what do you think? Well, the answer is yes, it's symmetric about the x-axis. Again, draw a line here. You can see that whatever's here will be here as well. Is it symmetric about the y-axis? Well, draw a line here. Take whatever's on this side and flip it over on this side. You see that these two will line up. So the answer is yes. Is this symmetric about the origin? The answer is also yes. Whatever you have here, rotate it to this side here, and you can see that these will line up. And then whatever you have here, rotate it and put it here, you'll see that this piece will line right on top of this piece here. So the answer is yes. Again, we can check by looking at the equation, and notice that we have squares. What's going to happen if we put negatives in for x or y, or for both? They're going to disappear. So you're going to see that this is symmetric about the x-axis, y-axis, and origin just because if you plug in negatives. So for the x-axis, if you plug in negative y for y, this will become y squared, and you get the original equation. For the y-axis, you plug in negative x for x. And this will become x squared, and you get the original equation. For the origin, you plug in negative x and negative y. But you see this becomes x squared and this becomes y squared, and you get the original equation. So it is symmetric about the x-axis, y-axis, and the origin. I think I have a couple more graphs. Here, I want to know, is this symmetric about the x-axis, y-axis, and origin? Let's start with symmetric about x-axis. That means you plug in negative y. Are you left with the original equation? The answer is no. If you get rid of this negative, you have to put it on this side. You're not going to get the same thing. So this is no. Is it symmetric about the y-axis? Well, that means plug in, so the original equation was y is equal to 1 over x. We're going to plug in negative x, so we get y is equal to 1 over negative x. But this negative doesn't disappear, so it's not symmetric about the y-axis. We have one more thing to test. Is it symmetric about the origin? And remember that the equation is y is equal to 1 over x. If I plug in negative y and I plug in negative x, well, this is now negative y is equal to, this negative can be moved up or onto the outside, so 1 over x. And then multiply both sides by a negative, you get the original equation. So it is symmetric about the origin. Now let me give you a visual of what this looks like. This graph, which we'll learn how to graph later, let me do a better job. It actually goes through the point 1, 1. So it's going to hit this point, and then it's going to have what we call an asymptote here and here. It's going to go through 1, negative 1. It's going to look something like this. So you can see that if you flip it along the x-axis, the mirror image is not going to be here. Along the y-axis, you're not going to get these two pieces aren't going to lay on top of each other. But if you rotate this one and put it here, you're going to get the same thing. So it is symmetric about the origin. The next one I have is y is equal to the square root of x. This one's actually a little tricky. The problem here is we can't take square roots of negative numbers. So there's actually there's not going to be anything involving negative x's on this side. We could graph this. I'm going to show you what the graph looks like. Look like this. And this is the entire graph. It stops right at 0, and then it goes this way forever. This graph, you can see, is not symmetric about the x-axis, the y-axis, or the origin. You can plug in negative y, and you see you don't get the same equation. If I move the negative to the other side, this is not the same. Remember, when we plug in negative y, that's checking to see if it's symmetric about the x-axis. We can't even plug in negative x in here because you can't take the square root of a negative 3 or anything like that. So it's not going to be symmetric about the y-axis because it's not even defined on that section of the graph of this plane. And if you can't plug in a negative x for anything other than 0, then putting in a negative y and a negative x, if that's not even possible, then you can't use that to check for symmetry about the origin, because you can't plug it in. So visually, you can see all three of these things. This is the best one to use for graphing. Let's look at one more example, and then we'll be done with symmetry. Here I have the absolute value function. So y is equal to the absolute value of x. You have to understand a few things about the absolute value function. Let's review. What is the absolute value of -3? Well, that's 3. What's the absolute value of 3? Well, that's also 3. What the absolute value function does is whenever you plug in a negative number, or any number, negative or positive, it always spits out the positive value. So if you plug in something like negative, let's do another number than 3. Let's do negative 1.97. You're going to get 1.97. And if you plug in, let's say 20, you're going to get 20. It just gives me the positive value. If it's already positive, then we just return that number. This graph is interesting. I'll show you what it looks like. It's kind of a little hard to draw, but for me to draw straight lines, but it's V-shaped. So it's V-shaped. For example, the point 1, 1 belongs on the graph. You can see that I went through 1, 1. This should go through 2, 2. It's a little off the side here, but it should be a straight line right here going through 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and so on. And the same thing over here. Sorry, it's a little, see if I can fix this. So you get the idea here. I can try to straighten this one up too. Like that. So it's V-shaped. And whatever you plug in for x, you're going to get the same thing for y. So x is going to be equal to y if its x is positive, greater than or equal to 0. And if you plug in negative x for x greater than or equal to 0, you're going to spit out the positive version. So like 1, 1 is on the graph, but also negative 1, 1 is on the graph. 2, 2 is on the graph, but negative 2, 2 is on the graph. Visually, you can see that this is symmetric about the y-axis. It's not symmetric about the x-axis, and it's not symmetric about the origin. We can test this. Let me write it up here again. This is symmetric about the y-axis. Plug in negative x. You get y is equal to the absolute value of negative x. But the absolute value of a negative is the positive. So you get the same thing. It's not symmetric about the x-axis or the origin, because when you plug in a negative y, that negative stays. We don't have absolute values on this side. So negative y equal to the absolute value of x would be y is equal to the negative absolute value of x, which is not the original here. And if you plug in negatives for both, the negative will go away here, but this negative will stay. So it's not symmetric about the origin. And you can see that by looking at the graph.